Hey guys, tonight we begin with something that will fundamentally change how you think about time itself. We're diving into one of the most mind-bending phenomena in physics, time dilation, where the faster you move, the slower time actually flows for you. This isn't science fiction. This is reality, and it's happening right now as you sit there watching this video. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Picture this. You're standing on a train platform watching two identical clocks. One sits beside you on the platform, ticking steadily. The other is mounted inside a train that's accelerating past you at incredible speeds. As that train rockets away, something extraordinary happens. The clock on the train begins to tick slower than yours. Not because it's broken, not because of some mechanical failure, but because time itself is actually running slower for that moving clock. This isn't theoretical. This is measurable, observable, and absolutely real. Welcome to the bizarre world of time dilation, where Einstein's theories collide with everyday reality in ways that feel impossible but are more true than the ground beneath your feet. Tonight, we're going to explore why speed doesn't just change where you are, it changes when you are. We'll uncover how astronauts age slower than their Earthbound twins, why GPS satellites need constant time corrections, and how the universe has been playing tricks with time since the very beginning. But here's what makes this even more fascinating. Time dilation isn't just happening to rockets and satellites. It's happening to you right now in ways you've never imagined. Every time you move, every time you accelerate, every time you simply exist in Earth's gravitational field, you're experiencing time dilation. The effects are tiny, nearly imperceptible, but they're there. And by the end of this series, you'll understand not just how it works, but why it had to work this way for our universe to exist at all. I'm going to walk you through the most counterintuitive concept in modern physics, using simple analogies, real-world examples, and mind-bending thought experiments that will leave you questioning everything you thought you knew about the nature of reality. We'll start with the basics, the foundation that Einstein built over a century ago, and then we'll venture into territory that even seasoned physicists find unsettling. But first, let me give you a glimpse of just how profound this really is. In 1971, physicists Haffel and Keating took 4 atomic clocks, the most precise timekeepers ever created, and flew them around the world on commercial airliners. When they landed, those clocks showed different times than identical clocks that had remained stationary on the ground. The difference was measured in nanoseconds, but it was exactly what Einstein's equations predicted. Time had literally moved at different rates for the flying clocks versus the earthbound ones. This wasn't just a clever experiment. It was proof that time is not the universal constant we once believed it to be. Time is flexible, malleable, and entirely dependent on motion and gravity. And tonight, we're going to dive deep into this rabbit hole to understand why the universe works this way and what it means for everything from space travel to the GPS in your phone. Now, before we go any further, I need to address something crucial. When most people first hear about time dilation, their immediate reaction is skepticism. How can time slow down? Time is just time, right? It flows the same for everyone, everywhere. That's common sense. But here's the thing about common sense. It's often wrong when it comes to the fundamental nature of reality. Common sense tells us the Earth is flat, that heavier objects fall faster, that light behaves like a wave or a particle, but not both. Common sense is built on our everyday experiences, and our everyday experiences don't include traveling at significant fractions of the speed of light. The reason time dilation seems impossible is because we live in a world of slow speeds and weak gravitational fields. The effects of relativity are so small in our daily lives that they're completely imperceptible. But make no mistake, they're always there, always acting, always shaping the flow of time around us. It's like trying to notice the curvature of the Earth while standing in a field. The curvature is real, but you need to step back and see the bigger picture to perceive it. So let's start with the foundation. To understand time dilation, we first need to understand what Einstein discovered about the nature of space and time itself. Before Einstein, we thought of space and time as separate entities. Space was the stage where events happened, and time was the universal clock that measured when they happened. Einstein showed us that this view was fundamentally wrong. Space and time are not separate, they're woven together into a single fabric called spacetime. Imagine spacetime as a stretched rubber sheet. Massive objects like stars and planets create dips and curves in this sheet. What we call gravity is actually objects following the curved paths created by these dips. But here's the crucial part. Time flows differently depending on where you are in this curved spacetime. The deeper you are in a gravitational well, the slower time moves. The faster you move through space, the slower you move through time. This brings us to one of the most important concepts in physics, the speed of light. Light travels at approximately 300 million meters per second in a vacuum, and this speed is absolute. It's the same for all observers, regardless of their motion. This might seem like a trivial fact, but it's actually the key to understanding why time dilation must exist. Here's where it gets weird. If you're traveling in a car at 60 miles per hour and you throw a ball forward at 30 miles per hour, someone standing on the sidewalk sees the ball moving at 90 miles per hour. Velocities add up. But light doesn't work this way. If you're traveling at half the speed of light and you shine a flashlight forward, the light doesn't travel at 1.5 times the speed of light. It travels at exactly the speed of light, no more, no less. This creates a paradox. How can light always travel at the same speed, regardless of the motion of its source? Einstein's answer was radical. Space and time themselves must adjust to keep the speed of light constant. If you're moving very fast, distances contract and time slows down just enough to ensure that light always travels at the same speed from your perspective. Let me give you a simple thought experiment to illustrate this. Imagine you're on a train moving at 90% the speed of light. You have a flashlight and you shine it toward the front of the train. From your perspective on the train, the light travels at the normal speed of light. But from the perspective of someone standing on the platform, how fast should that light be traveling? If velocities simply added up, it would be traveling at 190% the speed of light, which is impossible. The universe solves this problem by slowing down time for you on the train. From the platform observer's perspective, your clocks run slower, your movements are slower, even your thoughts are slower. But from your perspective, everything feels normal. The light from your flashlight travels at the normal speed of light, because time itself has slowed down to make it so. This is the essence of time dilation. It's not that clocks malfunction or that mechanical processes slow down. Time itself, the fundamental rate at which events unfold, changes based on motion and gravity. And this isn't just theory. We've measured it countless times with atomic clocks, particle accelerators, and astronomical observations. The mathematics behind this are surprisingly elegant. Einstein's equations show us that time dilation increases as you approach the speed of light. At everyday speeds, the effect is negligible. A person traveling at 60 miles per hour experiences time dilation of about 1 part in 10 to the 16th power. That's a difference of about 1 second every 300 million years. But as speeds increase, the effect becomes more dramatic. At 90% the speed of light, time slows down by a factor of about 2.3. This means that for every 2.3 seconds that pass for a stationary observer, only 1 second passes for the moving observer. At 99% the speed of light, time slows down by a factor of about 7. At 99.9% the speed of light, the factor is about 22. And as you approach the speed of light, time dilation approaches infinity. This creates some fascinating scenarios. Imagine a twin who travels to a distant star at near light speed while her sister stays on Earth. The traveling twin might experience the journey as taking only a few months, while decades pass on Earth. When she returns, she finds her sister has aged significantly more than she has. This is the famous twin paradox, and it's not really a paradox at all. It's a natural consequence of time dilation. But here's what makes this even more mind-bending. The traveling twin doesn't feel like time is moving slowly for her. From her perspective, her clocks tick normally. Her biological processes proceed at their usual rate, and the universe around her behaves exactly as she expects. It's only when she compares her experience to that of her earthbound sister that the difference becomes apparent. This brings us to one of the most important principles in relativity, the principle of relativity itself. There's no such thing as absolute motion. You can only measure motion relative to something else. When you're sitting in a smoothly moving train with the curtains closed, you can't tell whether the train is moving or the world outside is moving. Both perspectives are equally valid. The same principle applies to time dilation. If you're moving at high speed relative to me, I see your clocks running slow. But from your perspective, it's my clocks that are running slow. This seems contradictory, but it's not. The key is that we're both correct from our own reference frames. The apparent contradiction only arises when we try to reunite and compare our experiences directly. Now, you might be wondering how this relates to gravity. Einstein's genius was in recognizing that gravity and acceleration are fundamentally the same thing. If you're in a windowless elevator, you can't tell whether you're accelerating upward or sitting stationary in a gravitational field. This equivalence principle led Einstein to realize that gravity must also cause time dilation. The stronger the gravitational field, the slower time moves. This means that time runs slightly slower at sea level than it does on a mountaintop. The difference is tiny, about 10 nanoseconds per day for every meter of altitude, but it's measurable with atomic clocks. GPS satellites, orbiting about 20,000 kilometers above Earth, experience time dilation from both their motion and the weaker gravitational field at their altitude. Actually, let me tell you about GPS, because it's probably the most practical example of time dilation in your daily life. GPS satellites need to maintain incredibly precise timing to determine your location accurately. They do this by measuring the time it takes for signals to travel from multiple satellites to your receiver. But because these satellites are moving at about 14,000 kilometers per hour, and orbiting in Earth's weaker gravitational field, they experience time dilation. The motion of the satellites causes their clocks to run about 7 microseconds per day slower than clocks on Earth, but the weaker gravitational field causes their clocks to run about 45 microseconds per day faster than clocks on Earth. The net effect is that satellite clocks run about 38 microseconds per day faster than Earth clocks. This might seem like a tiny difference, but it would cause GPS errors of about 10 kilometers per day if not corrected. Engineers have to constantly adjust the satellite clocks to account for relativistic effects. Without these corrections, GPS would be completely useless within hours. Every time you use your phone to navigate, you're relying on Einstein's theories of relativity. It's a perfect example of how abstract physics concepts have very real, practical applications. But GPS is just the beginning. Time dilation affects everything from particle accelerators to the decay of cosmic rays in our atmosphere. When high-energy particles from space collide with our atmosphere, they create secondary particles called muons. These muons have very short lifespans, about 2.2 microseconds. At the speed they're traveling, they shouldn't be able to reach Earth's surface before decaying, but because they're moving at near light speed, time dilation extends their lifespans just enough for them to reach the ground, where we can detect them. This is direct evidence of time dilation happening in nature. The muons don't know they're experiencing time dilation. From their perspective, they live their normal lifespan and travel their normal distance, but from our perspective, they live longer and travel farther because time is running slower for them. These examples illustrate a crucial point about time dilation. It's not just a theoretical curiosity or a plot device for science fiction stories. It's a fundamental aspect of how our universe works. Every particle, every object, every living being experiences time dilation based on their motion and their position in gravitational fields. But here's where it gets even more interesting. Time dilation doesn't just affect mechanical clocks or particle decay. It affects biological processes, chemical reactions, and even the rate at which thoughts occur. If you could travel at near light speed, you wouldn't just age slower, you would think slower, react slower, and experience life at a different temporal rate than stationary observers. This raises profound questions about the nature of consciousness and experience. If time can slow down, what does that mean for our perception of reality? Are there aspects of time dilation that we haven't even discovered yet? And how does this connect to the broader structure of the universe? We're just getting started on this journey through the labyrinth of time. In the next part of this series, we'll explore the mathematical foundations of time dilation, dive deeper into the twin paradox, and examine some of the most extreme examples of time dilation in the universe. We'll visit black holes where time nearly stops, explore how time dilation affects the aging of stars, and investigate whether time travel might actually be possible. But before we go there, I want you to sit with what we've discussed tonight. Time, that most fundamental aspect of existence, is not what it seems. It's flexible, relative, and entirely dependent on motion and gravity. Every second of your life is shaped by relativistic effects that you can't feel, but that are always there. The next time you look at your watch, remember that it's not just measuring time, it's measuring your personal experience of time. And that experience is unique to you, shaped by your motion through space and your position in Earth's gravitational field. It's a reminder that reality is far stranger and more beautiful than our everyday intuition suggests. Now, let's push deeper into this rabbit hole. Because once you truly understand time dilation, you start to see the universe differently. You begin to realize that what we call the present moment isn't universal. There's no cosmic clock ticking away somewhere, keeping time for the entire universe. Instead, every observer has their own personal timeline, their own flow of time, shaped by their unique journey through space-time. This brings us to one of the most unsettling implications of time dilation. Simultaneity, the idea that events can happen at the same time, becomes meaningless on a cosmic scale. Two events that appear simultaneous to one observer might occur at different times for another observer moving at high speed. This isn't just a measurement problem or a communication delay. It's a fundamental feature of how time works in our universe. Let me give you a thought experiment that illustrates this beautifully. Imagine you're standing on Earth and you see two stars explode simultaneously in the night sky. The explosions appear to happen at exactly the same moment from your perspective. But now imagine an alien observer traveling at high speed relative to Earth. From their perspective, one star might explode hours or even days before the other. Both observations are correct. There's no universal truth about which explosion happened first. This relativity of simultaneity has profound implications for our understanding of causality. If there's no universal present, how can we define cause and effect? The answer lies in the structure of space-time itself. Events can only influence each other if they're connected by signals traveling at or below the speed of light. This creates what physicists call light cones, regions of space-time that define what can influence what. But I'm getting ahead of myself. Let's return to the more tangible aspects of time dilation. One of the most striking examples comes from the world of particle physics. When scientists accelerate particles to near light speed in machines like the Large Hadron Collider, they observe time dilation directly. Particles that would normally decay in microseconds suddenly live for much longer periods from our perspective. This isn't just an academic curiosity, it's essential for how particle accelerators work. The particles need to survive long enough to collide with other particles, and time dilation makes this possible. Without relativistic effects, most of the particles would decay before reaching their targets. Every discovery made in particle physics depends on our understanding of time dilation. The same principle applies to cosmic ray showers. When high-energy particles from deep space hit our atmosphere, they create cascades of secondary particles. Many of these particles are moving at velocities close to the speed of light. Without time dilation, they would decay before reaching Earth's surface. But because time runs slower for these fast-moving particles, they survive long enough to be detected by instruments on the ground. This creates a beautiful symmetry. The universe is constantly demonstrating Einstein's theories through natural phenomena. Every cosmic ray detection, every particle accelerator experiment, every GPS correction is evidence that time dilation is not just real but essential for the universe to function as it does. Now, let's talk about some of the more extreme examples of time dilation. Near black holes, where gravity becomes incredibly strong, time dilation reaches mind-bending extremes. As you approach the event horizon of a black hole, time slows down dramatically relative to distant observers. If you could somehow survive the journey, you might experience falling into the black hole as taking only a few minutes, while billions of years pass in the outside universe. This creates what physicists call the information paradox. If you fall into a black hole, do you disappear from the universe immediately, Or do you appear to freeze at the event horizon from the perspective of outside observers? The answer depends on whose reference frame you're using. From your perspective, you fall through the event horizon and presumably meet your doom at the singularity. From the outside universe's perspective, you appear to slow down and freeze at the event horizon, your image gradually fading as it gets redshifted into invisibility. Both perspectives are correct, but they seem to contradict each other. This is one of the deepest unsolved problems in modern physics, and it all stems from the relativistic nature of time. Time dilation doesn't just affect how we measure time, it affects the very structure of physical reality. But black holes aren't the only extreme example. Neutron stars, the collapsed cores of massive stars, also create significant time dilation effects. These objects are so dense that a sugar cube-sized piece would weigh as much as Mount Everest. Near the surface of a neutron star, time runs about 30% slower than it does in empty space. If you could somehow stand on the surface of a neutron star, you would age more slowly than your friends back on Earth. This might sound like science fiction, but it's observable reality. Astronomers can measure the time dilation effects around neutron stars by studying the behavior of matter falling onto their surfaces. The X-rays emitted by this infalling matter are shifted in frequency due to both gravitational redshift and time dilation effects. These observations provide direct evidence that Einstein's predictions about extreme gravity are correct. Even more fascinating are the implications for stellar evolution. As stars age and become more massive, they create stronger gravitational fields. This means that time runs slightly slower in the cores of massive stars compared to less massive ones. Over millions of years, this difference in the flow of time can affect how quickly nuclear reactions proceed, influencing the star's evolution and ultimate fate. Time dilation also plays a crucial role in the expansion of the universe itself. As light travels from distant galaxies to our telescopes, it passes through regions where time flows at different rates due to the gravitational effects of intervening matter. This creates subtle but measurable effects on the properties of the light we observe. Cosmologists must account for these relativistic effects when interpreting observations of distant objects. The deeper we look into space, the more time dilation effects we encounter. The most distant galaxies we can observe are so far away that their light has been traveling for billions of years to reach us. During this journey, the expansion of the universe has stretched both space and time. What we see when we look at these distant galaxies is not just how they appeared in the past, but how they appeared in a past where time itself flowed differently. This brings us to one of the most profound implications of time dilation. The universe has a history, a story that unfolds over cosmic time. But this history is not experienced uniformly by all observers. Different parts of the universe experience time at different rates, creating a complex tapestry of temporal experience that defies our intuitive understanding of how time should work. Consider the cosmic microwave background, the afterglow of the Big Bang that we can still observe today. This radiation has been traveling through space for nearly 14 billion years, and it carries information about the early universe. But the time dilation effects of the expanding universe mean that the events recorded in this radiation occurred in a cosmic reference frame where time flowed differently than it does today. This creates a fascinating paradox. The universe has a finite age, about 13.8 billion years. But because of time dilation effects, different observers can measure different ages for the same cosmic events. A hypothetical observer near a massive black hole might measure the age of the universe to be significantly different from our Earth-based measurements. Both measurements would be correct from their respective reference frames. Time dilation also affects our understanding of the ultimate fate of the universe. If the universe continues to expand forever, what happens to time itself? As matter becomes more and more dilute, gravitational time dilation effects become weaker and weaker. In the far future, when the universe is cold and empty, time might flow more uniformly than it does today. But even then, the expansion of space itself creates relativistic effects that influence how time flows. These cosmic implications of time dilation reveal something profound about the nature of reality. Time is not just a dimension in which events occur. It's a dynamic, flexible aspect of the universe that responds to matter, energy, and the curvature of space-time. Every massive object, every moving particle, every region of curved space contributes to the complex symphony of temporal flow that shapes our universe. But here's what makes this even more remarkable. Despite all this complexity, despite the fact that time flows differently for every observer in the universe, the laws of physics remain consistent. The speed of light is the same for all observers. The fundamental constants of nature are universal. The equations that govern how particles interact are the same whether you're on Earth or near a black hole. This universality of physical laws in the face of relative time is one of the most beautiful aspects of Einstein's theories. It suggests that there's a deeper unity underlying the apparent chaos of relativistic effects. The universe may be a place where time flows differently for different observers, but it's also a place where the fundamental structure of reality transcends these differences. As we wrap up this exploration of time dilation, I want you to consider the profound implications of what we've discussed. Time, that most basic aspect of existence, is not what it seems. It's not universal, not absolute, not independent of motion and gravity. Instead, it's a flexible, dynamic aspect of reality that shapes every moment of your existence in ways you can't directly perceive. The next time you use GPS, remember that you're relying on corrections for relativistic time dilation. The next time you see a star in the night sky, remember that the light reaching your eyes has been shaped by the time dilation effects of the star's gravity. The next time you feel the pull of Earth's gravity, remember that it's not just holding you down, it's also subtly slowing the flow of time around you. Time dilation isn't just a curiosity of modern physics, it's a fundamental feature of the universe that affects everything from the smallest particles to the largest structures in the cosmos. It's a reminder that reality is far stranger and more beautiful than our everyday experience suggests. And it's a window into the deep structure of space-time that governs everything we know and everything we can imagine. We've explored the foundations, but now let's dive into the mathematics that make time dilation not just possible, but inevitable. Don't worry, I'm not going to overwhelm you with complex equations. Instead, I want to show you the elegant simplicity behind what might be the most beautiful formula in physics. The key to understanding time dilation lies in something called the Lorentz factor, represented by the Greek letter gamma. This single number tells us exactly how much time slows down based on velocity. The formula is surprisingly simple. Gamma equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. Let me break this down in a way that makes sense. When you're moving slowly, say walking down the street, your velocity compared to the speed of light is essentially 0. So gamma equals 1 meaning time flows normally. But as your velocity increases toward the speed of light, something remarkable happens. The denominator of the equation gets smaller and smaller, making gamma larger and larger. At half the speed of light, gamma equals about 1.15, meaning time runs about 15% slower. At 90% the speed of light, gamma jumps to 2.29, so time runs less than half as fast. At 99% the speed of light, gamma reaches 7.09, meaning time crawls at 1/7 its normal rate. And here's the kicker: as you approach the speed of light, gamma approaches infinity. Time dilation becomes infinite. This mathematical relationship reveals something profound about the structure of the universe. The speed of light isn't just a speed limit for matter, it's a fundamental constant that determines how space and time behave. Nothing with mass can reach the speed of light because it would require infinite energy to accelerate that far. But more importantly, reaching the speed of light would mean time stops completely. Now let's explore what this means for actual space travel. Imagine you're planning a journey to Proxima Centauri, our nearest stellar neighbor, about 4.2 light-years away. If you travel at 10% the speed of light, the journey would take 42 years from Earth's perspective. But here's where it gets interesting. Time dilation at this speed is minimal, with gamma equal to about 1.05, so you'd only age about 3 weeks less than people on Earth. But what if you could travel at 90% the speed of light? The journey would take about 4.7 years from Earth's perspective. However, with gamma equal to 2.29, you would only experience about 2 years passing during the journey. You'd arrive at Proxima Centauri having aged only 2 years while 4.7 years passed on Earth. Push this to 99% the speed of light, and the effects become dramatic. The journey would take about 4.2 years from Earth's perspective, but you would only experience about 7 months passing. You'd arrive at our nearest star having aged less than a year, while over 4 years passed on Earth. This creates fascinating scenarios for interstellar travel. A journey to the center of our galaxy, about 26,000 light-years away, would take 26,000 years from Earth's perspective if you traveled at nearly the speed of light. But for the traveler, with sufficient time dilation, the journey might only feel like a few years or even months. But here's the catch, and it's a big one. The energy required to accelerate to these speeds increases dramatically as you approach the speed of light. At 90% the speed of light, you need about 2.3 times as much energy as classical physics would predict. At 99% the speed of light, you need about 7 times as much energy. And to reach the speed of light, you'd need infinite energy. This energy requirement isn't just a practical limitation, it's a fundamental feature of the universe. The same mathematics that give us time dilation also give us mass-energy equivalence. As you accelerate, your relativistic mass increases, requiring more and more energy to continue accelerating. This creates a natural speed limit that prevents anything with mass from reaching the speed of light. But let's step back from the extreme examples and look at time dilation in contexts that might seem more familiar. Commercial airline flights experience measurable time dilation effects. A typical transatlantic flight at 35,000 feet and 500 miles per hour experiences time dilation of about 1 part in 10 trillion. That's about 10 nanoseconds over an 8-hour flight. It sounds insignificant, but these effects are cumulative and measurable with atomic clocks. Flight attendants and pilots who spend their careers in the air actually age slightly less than people who remain on the ground. The difference is only a few microseconds over an entire career, but it's real and measurable. Even more fascinating is the time dilation experienced by the International Space Station. Orbiting at about 17,500 miles per hour at an altitude of roughly 250 miles, the ISS experiences both velocity-based time dilation and gravitational time dilation. The velocity effect causes time to run slower, while the reduced gravity causes time to run faster. The net effect is that astronauts on the ISS age about 0.01 seconds less per year than people on Earth. These examples illustrate an important point about time dilation. It's not just a theoretical curiosity or a plot device for science fiction. It's a measurable, observable phenomenon that affects everyone and everything in the universe. Every time you move, every time you change altitude, every time you accelerate, you're experiencing time dilation. Now, let's explore one of the most famous thought experiments in physics, the twin paradox. This scenario perfectly illustrates the counterintuitive nature of time dilation and resolves what seems like a logical contradiction. Imagine identical twins, Alice and Bob. Alice stays on Earth while Bob travels to a distant star at 90% the speed of light. The round trip takes 10 years from Earth's perspective. When Bob returns, he has aged only about 4.4 years due to time dilation, while Alice has aged the full 10 years. Bob is now 5.6 years younger than his twin sister. But here's where it gets tricky. From Bob's perspective during the journey, it's Alice who appears to be moving at 90% the speed of light. Shouldn't Alice's clocks appear to run slow from Bob's perspective? If both twins see the other's clocks running slowly, how can Bob be younger when they reunite? The resolution lies in the fact that the situation is not symmetric. Alice remains in a single reference frame throughout the journey, while Bob must accelerate to leave Earth, decelerate at the distant star, accelerate back toward Earth, and decelerate when he arrives. These acceleration phases break the symmetry and resolve the apparent paradox. During the periods when Bob is traveling at constant velocity, both twins observe the other's clocks running slowly. But during the acceleration phases, Bob observes Alice's clocks running fast, more than compensating for the slow periods. The net result is that Bob ages less than Alice, exactly as predicted by the mathematics of time dilation. This resolution of the twin paradox reveals something important about the nature of time dilation. It's not just about relative velocity, it's about the entire history of acceleration and deceleration. The twin who experiences acceleration is the one who ages less. This connects time dilation to the equivalence principle, the idea that acceleration and gravity are fundamentally the same phenomenon. Speaking of gravity, let's explore gravitational time dilation in more detail. Einstein's general theory of relativity predicts that time runs slower in stronger gravitational fields. This effect is separate from, but related to, the time dilation caused by motion. Both effects stem from the same underlying physics, the curvature of spacetime. The mathematics of gravitational time dilation are elegant in their simplicity. Time runs slower by a factor related to the gravitational potential. Near Earth's surface, the effect is tiny, about 1 part in 10 billion per meter of altitude. But near massive objects like neutron stars or black holes, the effect becomes dramatic. Consider a neutron star with a mass twice that of our Sun compressed into a sphere only 20 kilometers in diameter. The gravitational field at its surface is about 100 billion times stronger than Earth's gravity. Time at the surface of such a neutron star runs about 30% slower than time in empty space, far from any gravitational influence. This creates observable effects in the X-ray emissions from neutron stars. When matter falls onto the surface of a neutron star, it emits X-rays due to the intense heating from gravitational compression. These X-rays are red-shifted, meaning their frequency is reduced due to the time dilation effects of the neutron star's gravity. Astronomers can measure this redshift and use it to determine the mass and radius of the neutron star. But neutron stars are nothing compared to black holes. As you approach the event horizon of a black hole, gravitational time dilation becomes extreme. At the event horizon itself, time dilation becomes infinite from the perspective of a distant observer. This creates the paradoxical situation where, from the outside universe's perspective, nothing ever actually crosses the event horizon. Objects appear to slow down and freeze at the horizon, their images gradually fading as they get redshifted into invisibility. From the perspective of someone falling into the black hole, however, the experience is quite different. They pass through the event horizon in a finite amount of their own time, completely unaware that they appear frozen to outside observers. This is one of the most mind-bending aspects of general relativity, the idea that the same event can have completely different temporal characteristics depending on your reference frame. These extreme examples of time dilation near black holes have practical implications for our understanding of the universe. When astronomers observe matter falling into black holes, they must account for time dilation effects to correctly interpret what they're seeing. The accretion disks around black holes, those spiraling whirlpools of superheated matter, behave according to the laws of physics, modified by extreme time dilation. But let's bring this back to Earth and explore some more practical applications. The Global Positioning System provides perhaps the most everyday example of time dilation affecting technology. GPS satellites orbit at an altitude of about 20,200 kilometers, where Earth's gravity is weaker than at the surface. This causes their clocks to run about 45 microseconds per day, faster than clocks on Earth due to gravitational time dilation. But the satellites are also moving at about 14,000 kilometers per hour relative to Earth's surface. This motion causes their clocks to run about 7 microseconds per day slower than Earth clocks due to velocity-based time dilation. The net effect is that satellite clocks run about 38 microseconds per day faster than Earth clocks. This might seem like a tiny difference, but GPS requires nanosecond precision to determine your location accurately. A timing error of 38 microseconds per day would cause position errors of about 10 kilometers per day. Without constant corrections for relativistic effects, GPS would be completely useless within hours of activation. The engineers who designed GPS had to build these relativistic corrections into the system from the beginning. The satellite clocks are deliberately set to run slightly slow before launch, so that they keep perfect time once they reach orbit and experience the relativistic effects. It's a beautiful example of how abstract physics concepts become essential for practical technology. But GPS is just one example of how time dilation affects modern technology. Particle accelerators like the Large Hadron Collider rely on time dilation to function properly. When particles are accelerated to near light speeds, they experience significant time dilation. From our perspective, particles that would normally decay in microseconds live for much longer periods, allowing them to travel around the accelerator's 27-kilometer circumference multiple times before decaying. Without time dilation, most of the particles would decay before reaching their collision points. Every discovery in particle physics, from the Higgs boson to exotic subatomic particles, depends on our understanding of how time dilation affects particle lifetimes at high speeds. The same principle applies to cosmic ray detection. When high-energy particles from deep space collide with Earth's atmosphere, they create showers of secondary particles, including muons. These muons have very short lifespans, only about 2.2 microseconds. At the speeds they're traveling, classical physics predicts they should decay long before reaching Earth's surface, but time dilation extends their lifespans just enough for them to reach ground-based detectors. This allows scientists to study cosmic rays and learn about the most energetic processes in the universe. Every cosmic ray detection is evidence that time dilation is not just real, but essential for understanding the universe around us. These practical applications of time dilation reveal something profound about the nature of scientific knowledge. Theories that seem abstract and removed from everyday experience often turn out to have practical applications that transform our lives. Einstein's theories of relativity were originally pure theoretical physics, but they now underpin technologies we use every day. This connection between theory and application illustrates the power of mathematical physics. The same equations that describe time dilation near black holes also determine how GPS satellites must be calibrated. The same principles that govern the behavior of cosmic rays also explain how particle accelerators work. The universe operates according to consistent mathematical laws, regardless of the scale or context in which they're applied. But time dilation raises deeper questions about the nature of reality itself. If time is relative, if it flows differently for different observers, what does this mean for our understanding of existence? Are there aspects of reality that transcend the relativistic nature of time? And how do we reconcile our subjective experience of time with the objective reality of time dilation? These questions lead us into some of the deepest mysteries of modern physics. The relationship between time and consciousness, the nature of causality in a relativistic universe, and the possibility of time travel all emerge from our understanding of time dilation. But these are topics for deeper exploration, threads in the complex tapestry of spacetime that we're only beginning to unravel. As we prepare to venture even further into this labyrinth of time, remember that everything we've discussed tonight is not just theory. It's measurable, observable reality. Time dilation is happening all around you, all the time. Every GPS satellite, every cosmic ray, every particle in every accelerator is providing evidence that time is not what our intuition tells us it should be. The universe is stranger and more beautiful than we ever imagined, and time dilation is just the beginning of that strangeness. In our next exploration, we'll push even further into the extreme realms of space-time, where time dilation becomes so intense that it challenges our very concepts of existence and reality. But there's something even more extraordinary waiting for us in the depths of space, something that pushes time dilation to its absolute limits: black holes. These cosmic monsters don't just bend light and warp space, they torture time itself into unrecognizable forms. Near a black hole, time doesn't just slow down, it practically stops, and the closer you get to that point of no return, the event horizon, the more extreme the effects become. Let me paint you a picture of what this actually looks like. Imagine you're watching a friend fall toward a black hole. As they approach the event horizon, something bizarre happens. They begin to slow down from your perspective. Their movements become sluggish, their fall becomes a crawl, and eventually they appear to freeze completely at the horizon. Their image grows dimmer and redder as time dilation approaches infinity, until they fade from view entirely. But here's the mind-bending part. From your friend's perspective, none of this is happening. They fall through the event horizon in a perfectly normal amount of time, completely unaware that they appear frozen to the outside universe. They experience time flowing normally right up until they reach the singularity at the center. Two radically different experiences of the same event, both equally valid, both equally real. This is where Einstein's theories push us into territory that feels more like philosophy than physics. What does it mean for time to flow differently for different observers? If there's no universal clock, no cosmic timekeeper, then what defines the present moment? The answer is both simple and profound. There is no universal present. Every observer carries their own personal timeline, their own slice of now, shaped by their unique journey through space-time. Think about what this means for a moment. Right now, as you're listening to this, someone traveling at high speed relative to Earth experiences this moment differently than you do. An astronaut on the International Space Station is living in a slightly different present than you are. The difference is tiny, measured in fractions of seconds, but it's real. We're all living in our own personal timelines, synchronized enough for daily life, but fundamentally separate on the cosmic scale. This brings us to one of the most unsettling realizations in modern physics. Causality, the idea that causes precede effects, becomes complicated in a relativistic universe. If two events appear simultaneous to one observer but sequential to another, which observation is correct? The answer depends on whether the events can influence each other through signals traveling at the speed of light. Imagine two explosions happening on opposite sides of the galaxy. To you, they might appear simultaneous, but to an observer traveling at high speed, one explosion might appear to happen years before the other. Both observations are correct, but neither explosion can influence the other because they're too far apart for light signals to travel between them. The universe preserves causality by ensuring that only events within each other's light cones can have causal relationships. This creates a beautiful structure in spacetime called the light cone. Every event in the universe sits at the center of its own light cone, a region that defines what can influence it and what it can influence. The past light cone contains all events that could have affected the present moment. The future light cone contains all events that the present moment could potentially affect. Outside these cones lies a region where simultaneity is truly relative, where the order of events depends on the observer's motion. But let's step back from these cosmic implications and explore something more tangible. The technology in your pocket, your smartphone, relies on time dilation corrections in ways you might never have imagined. Not just GPS, but the fundamental operation of the device itself is governed by relativistic effects that occur at the quantum level. Inside your phone's processor, electrons are moving at significant fractions of the speed of light. At these speeds, relativistic effects become important for understanding how the device operates. The design of modern semiconductors must account for these effects to ensure proper operation. Every time you send a text, make a call, or check your email, you're relying on engineers' understanding of how time dilation affects the behavior of electrons in silicon. The same principle applies to particle accelerators used in medical treatments. When doctors use proton therapy to treat cancer, they accelerate protons to about 60% the speed of light. At these speeds, time dilation affects how the protons interact with tissue. Medical physicists must account for these relativistic effects to ensure the treatment is delivered precisely where it's needed. Even more fascinating is how time dilation affects the fundamental processes of life itself. The radioactive decay that powers our planet's core and drives plate tectonics is governed by quantum mechanics, but the rates of decay are affected by gravitational time dilation. Deep inside Earth, where gravity is stronger, radioactive elements decay at slightly different rates than they would on the surface. This creates a feedback loop where the planet's geology affects time, and time affects the planet's geology. The iron core of Earth, spinning in the planet's magnetic field, experiences time dilation effects that influence its magnetic properties. These effects are tiny, but they accumulate over geological timescales, potentially affecting the evolution of Earth's magnetic field over millions of years. But here's where it gets truly mind-bending. DNA replication, the fundamental process of life, occurs at the molecular level where quantum effects become important. The enzymes that copy DNA operate according to quantum mechanical principles that are influenced by time dilation effects. Every cell division, every heartbeat, every thought is subtly affected by the relativistic nature of time. This doesn't mean time dilation noticeably affects your daily life. The effects are far too small to perceive directly, but they're there, woven into the fabric of existence at the deepest level. You are a relativistic being living in a relativistic universe, even if you can't feel it. Now, let's explore what happens when we push time dilation to its theoretical limits. What if we could build a spacecraft capable of traveling at 99.9% the speed of light? The time dilation factor would be about 22, meaning that every year of travel time would correspond to 22 years passing on Earth. A journey to the center of our galaxy, normally requiring 26,000 years, would take only about 1 to 200 years from the traveler's perspective. But even this isn't the limit. At 99.99% the speed of light, the time dilation factor jumps to about 71. That galactic journey would take only about 370 years from the traveler's perspective. Push it to 99.999%, and the factor becomes about 224. The journey would take only about 116 years of traveler time, while over 26,000 years pass on Earth. These numbers reveal something profound about the structure of the universe. There's no theoretical limit to how much time can be dilated as long as you don't reach the speed of light itself. With sufficient energy and advanced technology, a traveler could potentially visit distant galaxies and return to Earth in a single lifetime, even though millions of years might pass on Earth during the journey. This creates fascinating scenarios for the future of space exploration. Generation ships, massive vessels designed to carry human populations on centuries-long journeys, might not be necessary if we can achieve sufficient time dilation. A small crew could potentially explore the galaxy and return to Earth within their natural lifespans, though they would find a dramatically changed world upon their return. But this also raises profound questions about the nature of human experience and continuity. If you could travel to a distant galaxy in what feels like a few decades, only to return and find that millions of years have passed on Earth, what would that mean for your connection to humanity? Would you still be human in any meaningful sense? Or would you have become something else entirely? A temporal refugee from a lost era? These questions push us beyond physics into philosophy and ethics. Time dilation doesn't just affect clocks and particles, it affects the very meaning of existence, identity, and continuity. If time is relative, then so is experience itself. Your entire life, from birth to death, is just one possible timeline among infinite possibilities, each equally valid from the perspective of space-time. But let's bring this back to the present moment and explore how time dilation affects our understanding of the universe's history. When we look at distant galaxies through our telescopes, we're seeing them as they were billions of years ago. But the light from these galaxies has travelled through regions of space-time with different gravitational fields and different rates of time flow. This means that the history of the universe is not a simple timeline, but a complex web of interrelated events occurring at different rates in different regions of space-time. The cosmic microwave background, the afterglow of the Big Bang, carries information about the early universe, but this information has been filtered through billions of years of time dilation effects as it travelled through the expanding cosmos. When cosmologists study the early universe, they must account for these effects to correctly interpret what they observe. The redshift of distant galaxies is not just due to the expansion of space, but also to the time dilation effects of the matter and energy that the light has encountered during its journey. Every observation of the distant universe is a lesson in relativity. This creates a beautiful paradox. The universe has a finite age, about 13.8 billion years. But because of time dilation, different regions of the universe have experienced different amounts of time since the Big Bang. Near massive objects like black holes, less time has passed. In the vast voids between galaxies where gravity is weak, more time has passed. The universe is not just expanding in space, it's expanding in time. And here's something that will really twist your mind. The expansion of the universe itself creates time dilation effects. As space stretches, it carries time along with it. The rate at which time flows depends not just on gravity and velocity, but on the expansion rate of the universe itself. We're living in a cosmos where time is literally being stretched by the expansion of space. This has profound implications for the ultimate fate of the universe. If the expansion continues to accelerate, driven by dark energy, then the time dilation effects will become more and more pronounced. In the far future, when the universe is cold and empty, time itself might flow differently than it does today. The heat death of the universe is not just the end of energy and matter, it's the end of time as we know it. But even more fascinating is what happens if the universe eventually stops expanding and begins to contract. During the contraction phase, time dilation effects would reverse. Regions that experienced slow time during expansion would experience fast time during contraction. The universe would not just collapse spatially, it would collapse temporally, with different regions experiencing the end times at different rates. These cosmic implications of time dilation reveal the deep connection between the largest scales of the universe and the smallest scales of quantum mechanics. The same mathematical principles that govern time dilation near black holes also determine how the universe evolves over cosmic time. The equations of general relativity link the behavior of individual particles to the fate of the entire cosmos. This brings us to one of the most active areas of research in modern physics, the search for a theory of quantum gravity. Time dilation, as described by general relativity, is a classical effect, but at the smallest scales, quantum mechanics becomes important. How does time dilation behave when quantum effects dominate? This is one of the deepest unsolved problems in physics. Some theories suggest that time itself might be quantized, made up of discrete units called Planck time intervals. If this is true, then time dilation would have a fundamental limit at the quantum scale. Other theories propose that time might be an emergent property of more fundamental quantum processes, not a basic feature of reality at all. These questions push us to the very limits of human knowledge and understanding. We're exploring territory where mathematics and physics meet philosophy and metaphysics. The nature of time, the structure of reality, the meaning of existence itself all emerge from our understanding of how time dilation works at the deepest level. But let's return to something more concrete and explore how time dilation affects the search for extraterrestrial life. If alien civilizations exist elsewhere in the galaxy, they would experience time at different rates depending on their location and motion. A civilization orbiting close to a massive star would experience time dilation effects that could significantly affect their development and evolution. Imagine trying to communicate with such a civilization. Radio signals sent from Earth might arrive at their planet compressed in time due to relativistic effects. What seems like a normal conversation to us might seem like rapid-fire chatter to them. Conversely, their responses might seem painfully slow from our perspective. The time dilation effects of their environment would create a fundamental barrier to communication. This raises fascinating questions about the nature of intelligence and consciousness in a relativistic universe. If thought processes are slowed down by time dilation, are the thoughts themselves different? Would a civilization experiencing strong time dilation effects think more slowly but perhaps more deeply, or would they develop entirely different forms of consciousness adapted to their temporal environment? These questions become even more intriguing when we consider the possibility of artificial intelligence. A computer program running on a spacecraft traveling at near light speed would experience time dilation just like any other physical process. The AI would think and process information at a rate that appears slow to outside observers, but normal from its own perspective. This creates the possibility of temporal AI, artificial intelligences designed to operate across different timescales. An AI system could potentially be programmed to experience time dilation as a feature rather than a limitation, allowing it to carry out long-term missions that would be impossible for biological beings. Such systems could serve as bridges between different temporal environments, translating between the fast time of planetary civilizations and the slow time of interstellar travel. But these technological possibilities also raise ethical questions about the nature of consciousness and identity in a relativistic universe. If an AI system experiences time dilation, does it have the same moral status as a biological consciousness? Are there rights and responsibilities that transcend the relativistic nature of time? These questions will become increasingly important as we develop more sophisticated AI systems and venture further into space. Now, let's explore one of the most speculative but fascinating aspects of time dilation, its potential connection to time travel. While traveling backward in time remains highly speculative and possibly impossible, time dilation provides a clear mechanism for traveling forward in time. Every high-speed journey is a journey into the future, allowing travelers to skip forward through time relative to their starting point. This creates interesting scenarios for future space exploration. A mission to a distant star system could serve as a form of time travel, allowing explorers to see how human civilization develops over centuries or millennia. They could launch their mission, travel to a distant star, and return to find Earth transformed by technological and social evolution. But this also creates paradoxes and ethical dilemmas. If you could travel forward in time through time dilation, would you have a responsibility to warn people about future disasters? Could you influence events that, from your perspective, have already happened? The causal structure of space-time becomes complex when time dilation allows for such dramatic temporal displacement. Some physicists have proposed that closed, time-like curves, paths through space-time that loop back to their starting point in time might be possible in extreme gravitational fields. These would represent true time travel, allowing travel to the past as well as the future. While such scenarios remain highly speculative, they illustrate how our understanding of time dilation continues to push the boundaries of what we think is possible. The mathematics of general relativity don't forbid closed time-like curves, but they require exotic conditions that may not exist in nature. Rotating black holes, cosmic strings, and other extreme objects might create the necessary space-time curvature, but the energy requirements and stability problems make such scenarios unlikely. Still, the fact that the equations allow for such possibilities shows how much we still don't understand about the nature of time and causality. As we push deeper into these speculative territories, we begin to see how time dilation connects to some of the deepest mysteries in physics. The nature of time itself, the structure of space-time, the relationship between quantum mechanics and gravity. All of these fundamental questions are illuminated by our understanding of how time flows differently for different observers. But perhaps the most profound implication of time dilation is what it tells us about the nature of existence itself. We are not just observers of the universe, we are participants in its temporal structure. Every moment of our lives contributes to the complex web of causality that defines reality. Our personal timelines are threads in the vast tapestry of space-time, each one unique but connected to all the others. This perspective transforms how we think about life, death, and meaning. If time is relative, then so is our existence within it. The moment you were born, the moment you will die, the entire arc of your life is just one possible path through space-time. From a cosmic perspective, your entire existence is simultaneous with the Big Bang, the formation of the first stars, and the ultimate fate of the universe. This doesn't diminish the meaning of your life, it enhances it. You are not just a temporary arrangement of atoms and energy, you are a permanent feature of space-time itself. Your existence has carved a unique path through the fabric of reality, a path that will always be there, always be real, always be part of the structure of the universe. Time dilation teaches us that the universe is not just stranger than we imagine, it's stranger than we can imagine. Every aspect of reality, from the largest galaxies to the smallest particles, is governed by principles that defy our everyday intuition. We live in a cosmos where time is flexible, where simultaneity is relative, where the very flow of existence depends on motion and gravity. As we continue our journey through this labyrinth of time, we'll explore even more extreme scenarios, even more mind-bending possibilities. We'll venture into the realm of quantum mechanics, where time itself might be quantized. We'll examine the latest research on black holes, where time dilation reaches its ultimate limits. And we'll investigate the cutting-edge theories that might finally unify our understanding of time with the other fundamental forces of nature. But for now, let this sink in. Time dilation is not just a curiosity of physics, it's a fundamental feature of reality that affects every aspect of existence. From the GPS in your phone to the cosmic radiation that bathes the Earth, from the fusion reactions in the sun to the quantum processes in your brain, everything operates according to the relativistic nature of time. The next time you look at a clock, remember that it's not just measuring time, it's measuring your personal experience of time, shaped by your motion through space and your position in Earth's gravitational field. You are living in your own unique temporal environment, slightly different from everyone else's, but connected to the vast network of space-time that encompasses all of existence. And as we prepare to dive even deeper into these mysteries, remember that we're not just learning about abstract physics concepts. We're uncovering the fundamental nature of reality itself, the hidden structure that underlies everything we know and everything we can imagine. Time dilation is the key that unlocks some of the deepest secrets of the universe, and we're just beginning to explore what those secrets might reveal. The journey through the labyrinth of time continues, and each step takes us further from our everyday intuitions and closer to the strange, beautiful, and utterly alien reality that is our universe. Time dilation is not just about clocks running slow or space travelers aging differently. It's about the very nature of existence in a cosmos where time itself is as dynamic and flexible as the space through which we move. In our next exploration, we'll push these concepts to their absolute limits, examining what happens when time dilation becomes so extreme that it challenges our very concepts of reality and existence. We'll explore the event horizons of black holes, where time itself breaks down, and investigate the latest theories about the quantum nature of time. The rabbit hole goes deeper, and the revelations waiting for us are more profound than anything we've encountered so far. But here's where time dilation becomes truly extraordinary. We've been talking about extreme speeds and massive objects, but time dilation is happening to you right now, at this very moment, in ways that would have seemed impossible just a century ago. Your head is aging faster than your feet. Not by much, about 90 billionths of a second over an entire lifetime, but it's measurable with atomic clocks. The difference in gravitational field between your head and your feet, a mere 2 meters of altitude, is enough to create detectable time dilation. This isn't just a curiosity, it's a reminder that you exist in a gradient of time, where every inch of altitude corresponds to a slightly different rate of temporal flow. Your body is a living experiment in relativity, stretched across different rates of time from head to toe. The blood flowing through your arteries experiences infinitesimally different time rates depending on whether it's in your brain or your heart. Now, let's venture into something that will completely reshape how you think about the nature of time itself. What if I told you that time dilation doesn't just affect how fast time flows, but actually determines whether events exist at all? This brings us to the concept of the relativity of simultaneity, one of the most unsettling discoveries in all of physics. Imagine you're standing on a train platform, watching a train speed by at a significant fraction of the speed of light. On that train, someone drops a ball at the exact moment they turn on a flashlight. From your perspective on the platform, these events don't happen simultaneously. The ball might drop first, then the flashlight turns on, or vice versa, depending on the train's direction and speed. Both events happen, but their order depends entirely on your motion relative to the train. This isn't just a measurement problem or a quirk of observation, it's a fundamental feature of how the universe works. There is no universal present moment, no cosmic clock ticking away somewhere in the depths of space. The very concept of now is personal, private, and utterly dependent on your motion through space-time. Think about what this means for reality itself. Right now, as you listen to this, somewhere in the universe, an alien civilization might be experiencing an event that, from their perspective, is happening simultaneously with this moment. But from another observer's perspective, that same event might have happened 1,000,000 years ago or won't happen for 1,000,000 years in the future. All three perspectives are equally valid, equally real, equally true. This creates what physicists call the block universe theory. If simultaneity is relative, then past, present, and future all exist simultaneously from some perspective. Your birth, your death, and every moment in between are all equally real, just located at different coordinates in space-time. The universe is not a movie playing frame by frame. It's a sculpture where every moment exists eternally, frozen in the amber of space-time. This perspective transforms how we think about free will, destiny, and the nature of existence itself. If all moments exist simultaneously, are we truly making choices, or are we simply following paths that already exist in the structure of space-time? These questions push us beyond physics into philosophy, but they emerge directly from our understanding of time dilation and the relativity of simultaneity. But let's ground this in something more tangible. The Large Hadron Collider, that magnificent machine buried beneath the Swiss-French border, is actually a time machine, not in the science fiction sense, but in the very real sense that it creates conditions where time dilation becomes extreme. When protons are accelerated to 99.99991%, the speed of light, they experience time dilation factors of over 7,000. From our perspective, these protons race around the 27-kilometer ring about 11,000 times per second. But from the proton's perspective, the journey around the ring takes much longer in their personal time. The entire structure of the accelerator is contracted in their reference frame, appearing only about 4 meters long instead of 27 kilometers. They experience the collision with other protons in their own time frame, completely unaware that we see them as moving at nearly the speed of light. Every collision in the LHC is a demonstration of time dilation in action. The exotic particles created in these collisions have extremely short lifespans, measured in tiny fractions of a second, but time dilation extends their lives just enough for our detectors to register them. Without relativity, particle physics would be impossible. The Higgs boson, the particle that gives mass to all other particles, was only discoverable because time dilation allowed it to exist long enough to be detected. This connects to something profound about the nature of mass itself. Einstein's famous equation, E = mc2, is intimately connected to time dilation. As objects approach the speed of light, their relativistic mass increases, requiring more and more energy to accelerate them further. This isn't just a mathematical curiosity, it's the reason the speed of light is an absolute limit for anything with mass. But here's where it gets really interesting. Massless particles like photons always travel at the speed of light, which means they experience infinite time dilation. From a photon's perspective, no time passes at all during its journey. A photon created in the core of the Sun experiences its 8-minute journey to Earth as instantaneous. From the photon's reference frame, it is created and absorbed in the same moment, regardless of how far it travels. This creates a beautiful paradox. Light, which seems to connect all parts of the universe instantaneously, actually exists outside of time as we understand it. Every photon carries information from its creation to its absorption without experiencing any passage of time. The light hitting your eyes right now from a distant star was created billions of years ago, but from the photon's perspective, it's arriving at the same instant it was created. This gives us a new way to think about the universe's structure. Space and time are not separate entities, they're unified in space-time. But light, which travels at the speed that links space and time, exists in a realm where this distinction becomes meaningless. Photons are the messengers of space-time, carrying information across vast distances without experiencing the passage of time. Now, let's explore how this connects to one of the most active areas of modern physics research, the search for gravitational waves. These ripples in space-time itself travel at the speed of light, carrying information about the most violent events in the universe. When two black holes collide, they create gravitational waves that propagate outward at light speed, carrying away energy and angular momentum. But here's the fascinating part. These gravitational waves are literally oscillations in time itself. As they pass through Earth, they alternately speed up and slow down the flow of time by infinitesimal amounts. The LIGO detectors that first observed gravitational waves are actually measuring time dilation effects so small that they would be undetectable by any other means. When a gravitational wave passes through the detector, it stretches and compresses space, but it also stretches and compresses time. The laser beams in the detector travel slightly different distances, not just because space is warped, but because time is flowing at slightly different rates in different parts of the apparatus. We're literally listening to the universe's song by measuring the rhythm of time itself. This brings us to something that might seem like science fiction, but is actually cutting-edge physics research. Scientists are now developing gravitational wave detectors that could potentially detect the time dilation effects of dark matter. If dark matter particles interact gravitationally, they should create tiny fluctuations in the rate of time flow that might be detectable with sufficiently sensitive instruments. This would revolutionize our understanding of the universe's structure. Dark matter makes up about 27% of the universe's mass energy, but we've never directly detected it. If we could measure its gravitational effects on time itself, we might finally understand what this mysterious component of the universe actually is. But let's push even further into speculative territory. Some theories suggest that time dilation might be connected to the expansion of the universe itself. As space expands, it carries time along with it, creating a kind of temporal stretching that affects how we perceive the age and size of the cosmos. This could explain some of the puzzles in modern cosmology, like why the universe appears to be accelerating in its expansion. The connection between time dilation and cosmic expansion raises profound questions about the nature of time on the largest scales. If the universe is expanding, is time expanding with it? Are we living in a cosmos where not only space but time itself is growing larger? These questions push us to the very limits of our understanding of reality. Consider what this means for the ultimate fate of the universe. If time dilation effects become more pronounced as the universe expands, then the far future might be a place where time flows very differently than it does today. The heat death of the universe, that distant epoch when all the stars have burned out and entropy has reached its maximum, might not be experienced uniformly by all observers. Some regions of the universe might reach heat death quickly, while others, protected by time dilation effects, might continue to experience relatively normal time flow long after the rest of the cosmos has gone cold. This could create islands of time in an ocean of cosmic stillness, pockets of temporal activity in a universe that has otherwise run down. But here's something even more mind-bending. Recent research suggests that time dilation might play a role in the formation of large-scale structures in the universe. The cosmic web, that vast network of galaxies and galaxy clusters connected by dark matter filaments, might be shaped partly by relativistic effects that we're only now beginning to understand. When the universe was young and dense, time dilation effects were much more pronounced than they are today. Regions of higher density experienced slower time flow, which could have affected how matter clumped together to form the first stars and galaxies. The universe's structure might literally be a fossil record of ancient time dilation effects, preserved in the distribution of matter across cosmic scales. This connects to one of the most exciting frontiers in modern physics, the intersection of quantum mechanics and general relativity. At the smallest scales, quantum effects become important, and the nature of time itself might be fundamentally different from what we observe at larger scales. Some theories suggest that time might be quantized, made up of discrete units that can't be subdivided further. The implications of time dilation extend far beyond theoretical physics into the very heart of what it means to be human in an infinite universe. As we stand at this crossroads of understanding, we're forced to confront questions that would have been unimaginable just a century ago. What does it mean to exist in a cosmos where time itself is malleable? How do we find meaning and purpose when our entire experience of reality is shaped by forces we can barely comprehend? These aren't just philosophical abstractions. They're practical questions that will define the future of human civilization as we venture beyond Earth. Every step we take into the cosmos is a step into a realm where our intuitions about time and space become not just inadequate, but dangerously misleading. The universe doesn't care about our common sense. It operates according to laws that are beautiful, elegant, and utterly alien to our everyday experience. Consider the profound loneliness that time dilation creates. If you could travel to the nearest star and back at near light speed, you might age only a few months while decades pass on Earth. Everyone you've ever known, everyone you've ever loved, would be gone by the time you return. You would be a temporal orphan, displaced not just in space, but in time itself. This is the price of pushing against the cosmic speed limit, the cost of dancing with the fundamental forces that govern reality. But there's also beauty in this isolation. You would carry within you the memories of a world that no longer exists, the living repository of a lost moment in human history. In a universe where time is relative, memory becomes the only true constant. The experiences locked in your mind would be more permanent than mountains, more enduring than stars. You would be a walking monument to the fluidity of time itself. This brings us to something that might seem impossible, but is actually inevitable. As human civilization spreads throughout the galaxy, we will fragment not just across space, but across time. Different populations will experience history at different rates, creating a complex temporal ecosystem where the past, present, and future become deeply personal concepts. A message sent between star systems won't just travel through space, it will travel through time, arriving in a future that the sender can barely imagine. The children born on high-speed generation ships will grow up in a universe where time moves differently than it does for their Earth-bound cousins. They will develop cultures, languages, and ways of thinking that are shaped by their unique temporal environment. Over generations, these differences will compound, creating branches of humanity that are separated not just by distance, but by the very flow of time itself. This temporal fragmentation isn't a bug in the cosmic operating system, it's a feature. Time dilation might be the universe's way of ensuring that life and consciousness can survive on multiple timescales simultaneously. If a catastrophic event destroys one temporal branch of humanity, others will continue to exist, preserved in their own unique flows of time. We won't just be backing up our civilization across space, we'll be backing it up across time. But perhaps the most profound implication of time dilation is what it reveals about the nature of existence itself. We are not separate from the universe, observing it from the outside. We are part of its structure, woven into the fabric of space-time itself. Every heartbeat, every thought, every moment of consciousness contributes to the cosmic symphony of temporal experience. We are not just in the universe, we are the universe becoming aware of itself. This awareness carries with it a responsibility. We are the custodians of time, the guardians of temporal experience in a cosmos that might otherwise be cold and lifeless. Our consciousness, our ability to perceive the flow of time, might be the most precious thing in the universe. It's what transforms the mechanical ticking of cosmic clocks into the rich, meaningful experience of existence itself. As we've journeyed through this labyrinth of time, we've discovered that reality is far stranger and more beautiful than we ever imagined. Time dilation isn't just a curiosity of physics, it's a window into the fundamental nature of existence. It shows us that the universe is not a machine grinding away according to predetermined laws, but a living, breathing entity where time itself dances to the rhythm of matter and energy. The next time you look up at the stars, remember that you're not just seeing distant suns, you're seeing different moments in the cosmic flow of time. Each star exists in its own temporal environment. Each galaxy experiences time at its own rate. The universe is not just vast in space, it's vast in time, a four-dimensional tapestry where every thread represents a unique temporal experience. And you, sitting there in your own personal bubble of space-time, are part of this cosmic dance. Your existence, however brief it might seem, has carved a permanent path through the fabric of reality. You are not just a temporary arrangement of atoms and energy, you are a permanent feature of the universe's temporal landscape. Your timeline, your personal experience of time's passage, is as real and enduring as the stars themselves. This is the ultimate lesson of time dilation. We are not victims of time, we are its co-creators. Every choice we make, every path we take, every moment we experience contributes to the vast, complex, ever-evolving structure of space-time. We are not just living in the universe, we are helping to write its story, one moment at a time. The labyrinth of time stretches infinitely in all directions, filled with wonders we can barely imagine and mysteries we have yet to solve. But we are not lost in this maze. We are explorers, pioneers of temporal understanding, pushing ever deeper into the heart of reality itself. With each step, we discover new aspects of the cosmic dance, new ways that time and space interweave to create the rich tapestry of existence. Time dilation has shown us that the universe is not just stranger than we imagine, it's stranger than we can imagine. But it's also more beautiful, more elegant, and more deeply interconnected than we ever dared to dream. We are part of something magnificent, something that transcends our everyday experience and connects us to the deepest structures of reality itself. As we continue our journey through the cosmos, as we push against the boundaries of space and time, we carry with us the knowledge that we are not just explorers of the universe, we are the universe exploring itself. Time dilation is not just a physical phenomenon, it's a reminder that we are part of the cosmic story, temporal beings in a temporal universe, dancing together in the endless, beautiful, mysterious flow of time itself. The adventure is just beginning. The labyrinth of time stretches ahead of us, infinite and inviting, filled with wonders beyond our wildest imagination. And we, armed with our understanding of time dilation, are ready to explore every twist and turn, every hidden passage, every secret chamber in the vast cathedral of space-time. The universe is waiting, and time itself is our guide.